So independent sampling actually does not require any spatial procedure that we need to be careful. And you see, we say that when two systems are simulated with different random number streams and in different number of replications, let's just say M1 and M2, then we are going to assume independent sampling. Actually, even if the replication numbers are the same, if the random number streams are different, again, it is going to be independent sampling, okay? So M1 and M2 can be any two number of replications. It doesn't matter, but it says in order to get a reliable result for independent sampling, we definitely need to have a number of replications which is greater than or equal to 6. Now, the theoretical variance of the replication means, if you remember, is sigma square 1 over m1, and the variance of the second system, so y dot 2, is sigma square 2 over m2. So remember, sigma 1 square is the theoretical variance across the replications of the first system design, and sigma 2 square is the theoretical variance across the replications for the second system design. So this 1 here and 2 here after the dots, it is indicating that this belongs to first system and this belongs to second system. Now, these are the theoretical variances. I mean, it is impossible for us to calculate these theoretical variances, but we know that theoretically, the variance of our final estimate is going to be equal to the theoretical variance across replications divided by the number of replications in each system design. Okay. Now, in the end of the test, I am going to check that value. What is the difference between the performance metric in the first system and in the second system? And in order to draw a confidence interval for that difference, I am going to check the variance of the performance statistic that I obtained from the first system minus the performance that I have obtained in the second system. And if you remember the probability theory, the variance of the difference between two random variables is equal to the variance of the first random variable plus the variance of the second random variable minus 2 times the covariance of these random variables. Now, we know that these two simulations are run independently using different random number streams. Therefore, the covariance should be assumed as 0. So there should not be any covariance because both systems are using different random number sequences. Because of that reason, we can say that the variance of the difference is simply equal to the sum of the variances, the variance of the first system plus the variance of the second system, not minus. Please be careful. Therefore, the variance of the difference of the outputs is equal to the sum of the theoretical variances. The covariance is 0 due to the independent sampling. Now, I am just going to develop a framework for the independent sampling procedure. So let's just say I have the first system and the second system here. And these values, y bar values, are the replication averages. So my first replication, my second replication, my third replication. Now this time, the replications are given in the columns. And in the rows, I have the first system and the second system. So y bar 1, 1 means what? Under the first system design, the average in my first replication. So I do not see the within replication data here. I only see the replication averages. Under the first system design, I have the first replication average in y bar 1, 1. Under the first system design, I have the second replication average, which is y bar 2, 1. So the first index here shows me the replication number. The second index shows me the system that I choose, the first system or the second system. Now, if I take the averages of across the replications here, the sample mean of these replications will give me the estimate for the performance metric under the first system design, which is y bar dot 1, and y bar dot 2 is the estimate for the performance metric under the second system design. And I can also calculate the sample variance across the replications as S1 square and S2 square for the first and the second system design respectively. Now, the true performance metrics are the expectations of these values, if you remember. The expected value of the replication average under the first system design is theta 1, and the expected value of the replication average under system design 2 is the performance metric in the system design 2. So my example was expected queue times. So expected time spent in the queue, my performance metric was this. And here we can say that if the confidence interval of theta 1 minus theta 2 is in the negative region, so if the 95% confidence interval developed for theta 1 minus theta 2 is in the negative region, which means all values in the confidence interval are negative, in that case we say that theta 1 is less than theta 2 and system 1 is better. Okay? If the confidence interval developed for theta 1 minus theta 2 is in the positive region, in that case with 95% confidence level, theta 1 is always greater than theta 2. This means the second system is better. Why? Because we are attracted by low expected Q time. And finally, if the confidence interval that you develop for theta 1 minus theta 2 contains 0 in it, the comparison will be inconclusive because there will be not enough evidence to reject the null hypothesis. So the null hypothesis is what? The both theta 1 and theta 2 are equal to each other. So there is not a significant difference between the two systems. This is the null hypothesis. Now, how do we build a confidence interval for independently sampled simulation runs? So let's just say this is the average across replications for the first system design. This is the average across replication for the second system design. This is the sample variance across replications for the first system design, and this is the sample variance across replications for the second system design. N1 and N2 are respectively the number of replications in each system design. So we take the square root of these values, so variance of the system design 1 divided by M1 plus the variance of system design 2 divided by M2, and we have a T quantile here. Again, if you're interested in a 95% confidence interval, you need to check the 0.025 quantile for the T distribution's tail, and the degrees of freedom must be calculated with this formulation, my friends. So I know it's a very complicated formulation, it seems like as it is, but actually it is very close to M1 plus M2 minus 2. But the theoretical true degrees of freedom parameter that you need to select is the closest integer to that value. So you identify that complicated value, and the closest integer to that value can be taken as degrees of freedom parameter here. And the sample variances across replications can be calculated with these formulations once again. So let's practice this. So we have the average Q waiting times obtained in the replications of two alternative system designs here. In the first system design, I have 7 replications, M1 is 7, and in the second system design, I have 6 replications, M2 is 6. In each replication, I have obtained the average Q waiting times of the clients. So in the first replication of the first system design, it is 5.44. In the second replication, it is 4.86, so on and so forth. And in the second system design, the first replication ends up with an average Q waiting time of 6.03. In the second replication, 5.94. Again, it goes like this. Now, in order to prevent hard work, I have already calculated the sample mean for these 7 replications. So this is the average across replications under the first system design, and this is the average across replications under the second system design. I mean, just by looking at these sample means, you see that the average Q waiting time under the second system seems to be larger than the average waiting times of the first system. So without looking at the variances, you may end up thinking like the second system is worse than the first one. So the first one is better because the average Q waiting time is less. But I mean, we should not come up with these certain conclusions without running a statistical testing procedure, right? Because we also have the sample variances of these replications. So this is the sample variance obtained by 7 replications by using this first formula. Basically, we subtract the sample mean from all these 7 values and square the differences. The sum of the squared differences is divided to 6 because m1 minus 1 is 6. And in the second sample variance calculation, we subtract the sample mean from every 6 value here. The differences are squared and summed up, and we divide this summation to 5, which is 6 minus 1. So the sample variances are also calculated. The sample averages and the sample variances across replications are already calculated and present here. Under a 95% confidence level, test if any system yields a significantly less expected waiting time in the queue. So here in this question, we need to assume that there is an independent sampling between the two system designs here. So we are not using common random numbers in the replications, in the same replications of the different systems. So we are going to run a basic t-test here, but not in the form of a t-test. We are just going to develop a confidence interval for the difference between the first system and the second system. Now, I want to construct a 95% confidence interval for theta 1 minus theta 2. The expected queue time in the first system minus the expected queue waiting time in the second system, or just waiting times. And my confidence level is 95%, so my significant level is 0.05. So let's start by calculating the degrees of freedom. So according to the formulation that I have shown you at page 8, I'm just going to plug in these sample variance values and M1 and M2 values in this formulation, and it is going to give me a 10.874, and when you calculate its closest integer, you get 11. Now, as I have told you, my friends, actually that value here is usually very close to M1 plus M2 minus 2, as I have told you. What is M1? M1 is 7, M2 is 6, M1 plus M2 is 13, 13 minus 2 is 11. Now, in the statistics course, maybe you have seen it like this, and I believe you if you say that like that. Actually, the true degrees of freedom that you need to use should be calculated like this, and for small values of replications, it is usually going to be very close to M1 plus M2 minus 2, but if the values are large, again, it doesn't matter, because when the degrees of freedom goes to infinity, if you remember, the t quantiles are converging to z quantiles in any way. It is therefore in the statistics course, you have learned about this as M1 plus M2 minus 2. But actually, the true degrees of freedom that I need to use should be calculated like this, according to the theory. So the t quantile for a alpha over 2 value as 0.025 and degrees of freedom 11 is 2.20 for quantile value of 0.025, and for degrees of freedom parameter 11, my t quantile value is 2.20, and my differences between the sample means from the first sample mean to the second sample mean, it is going to be 5.243 minus 5.968. And then I am going to write plus minus the t quantile that I have written, square root of the sample variance across replications under the first system design divided by M1, which is 7, plus the sample variance across replications under the second system design, which is 0.054, divided by the number of replications. And then this confidence interval, you see, it is all in the negative region. So with 95% confidence level, we can say that the difference between theta 1 and theta 2 is going to be negative, which means system 1 seems to have a statistically significantly less expected queue time. Therefore, the average waiting time in the queue in the system 1 seems to be significantly less. Therefore, I should say that system 1 is better as a conclusion of this procedure.